Alright, so here's my code. Here's a demonstration, a two-dimensional demonstration of how the algorithm works in practice. So I've downloaded a bunch of images to feed them into the data to sort of demonstrate its capabilities. I am going to transform the data into a sort of Gaussian distribution, sort of transform the values until it becomes a Gaussian. And then I have a very unoptimized implementation of my algorithm. And then I have I take the Gaussianized data, I put into matrix, these are in the wrong order. I sort of mix them up using a uniform or random matrix, and then I process it by taking the PCA, and then I remix it in order to give that kind of very steep contrasting mapping that I talked about in my presentation. So let's run this. Here's my algorithm, and it actually tells you how well it did. It did quite poorly, so I'm gonna do this again. My algorithm's not very good right now. It kind of gets caught up, it's very buggy, but the good thing is it tells you how well it did. So if it did poorly, I'm just going to rerun it. Here we got very good results. So we're gonna run the test. So we have the original images, we have the mixture of them, and as a benchmark comparison, here's how independent component analysis did, and this is how my algorithm did. Let's run that again using new permutations. And here's how my algorithm did. And we have a bunch of different images, so let's go through, a bunch of combinations of them. We get okay results. I'm just gonna run this, if I feed this, it's not gonna be terrible, but we're really looking for some very good results here. That's good enough. And it separates them quite nicely, I think. Especially for a task that was considered theoretically impossible to do. Here we get very good results. And the corresponding output is similarly very, very good. Let's enter new data. Very good results. Very good output. Once again, high confidence, and we're going to get great results. Now, in those cases where it kind of hiccuped and gave a very poor slope, it's not because the optimal solution doesn't exist. It's just that the sort of, I'm assuming the algorithm kind of hiccups on local minimums or something like that. I'm not very sure. I try to prevent that, but that's just going to be a problem that's going to be dealt with later. Here's my original images, here's the mixtures, here's how independent component analysis does. I'm being harsh on it by feeding it data that it knows it's not able to separate. But it's sort of to demonstrate that we're not exploiting very minuscule differences between the pure Gaussian distribution and sort of an imperfect Gaussian distribution. I'm just using the standard algorithm as a comparison. Let's run this again. Here we get results that are not so good, and as a result, we just get a little bit of interference. Once again, here we got caught up in another local maximum, presumably. Here the results are going to be atrocious. I'll tell you, they are. Great results and great output. So this this algorithm also works for non-Gaussian distributions. But I guess if you I can as a point use them, test it on non-Gaussian distributions. But we already have algorithms for non-Gaussian distributions. The beauty of this algorithm is that it does not rely on any specific assumptions. The only statistic it takes is like the correlations between the mixtures. That's the only thing it looks at. There we go. I hope that's a sort of good enough demonstration of this algorithm. Thank you for watching.